Swayam Prabha. Digital India. Educated India.
Okay, welcome back to the lectures on advanced calculus for engineers, and this is lecture number 2 of module 1, and here we will be talking about mean value theorems. So again, this lecture belongs to the single variable calculus, where we will study the Lagrange mean value theorem, Cauchy mean value theorem, and some worked problems. So in the previous lecture, what we have seen, the Rowe's theorem, which says that if a function f is continuous in the closed interval a b, differentiable in the open interval a b, and the function value at a and b, these 2 points, is equal, then there exists a number c in the open interval a b where the function derivative vanishes. So here we will go with the further extension to this Rowe's theorem, and the so called the first theorem which we will see here, that is the Lagrange mean value theorem. So the statement of the Lagrange mean value theorem says that if a function f is continuous in the closed interval a b, so this is same hypothesis as we have in the Rowe's theorem, and then the function is differentiable in the open interval a b, so that is also same as before. But there is no third hypothesis which was like f a is equal to f b. So therefore it is more generalized. So this is the generalized version of the Rowe's theorem. So here the conclusion is that there exists a number c in the open interval a b such that the f b minus f a over b minus a, so this quotient f b minus f a divided by this b minus a, this is equal to f c, this is equal to f prime c. So the derivative of the function at some point c. So again there will exist a number c in the open interval a b such that this f prime c will be equal to f b minus f c over b minus a. So what is the geometrical interpretation of this? So suppose we have this function which is continuous and differentiable. This is f a here, and then we have f b there. So if we join this a and b, so there will be a line joining these 2 points, and what will be the slope of this line? F b minus f a over b minus a. So that is the slope of this line joining these 2 points, and this theorem says that there will be at least one point in the open interval where the slope will be equal to the slope of this line here, what we have. So as you can see in this particular example, that indeed there is a point here where you will see that this is slope of this line is equal. Here also the slope of this line will be equal to the slope of this line, and at this point also we will have the slope of this line equal to this one. So that is the Lagrange mean value theorem. As we will see in a minute that this is more generalized version of the Rowe's theorem. So there is at least one tangent line in the interval that is parallel to the line segment that goes through the end points of the curve. So this is the physical interpretation, geometrical interpretation of this Lagrange mean value theorem. getting into the proof of the Lagrange mean value theorem, it is simple, because here we will be using the Rose theorem to prove the Lagrange mean value theorem, and the idea is that we define a auxiliary function. What is that auxiliary function? Here we consider this phi x a function which is equal to fx minus fb minus fa over b minus a, that slope which we was talking about, and into x. So, we have considered a auxiliary function. This auxiliary function will help us to prove the statement of the Lagrange mean value theorem. So, what is the property of this function we have? This function phi satisfies all the conditions of the Rose theorem. Why it satisfies all the condition of the Rose theorem? So, suppose first condition was the continuity in the closed interval a and b. So, considering the continuity, so f is continuous, this is continuous as per our assumption of the mean value theorem, the Lagrange mean value theorem. This is some constant here, so we are not worrying about it, and this is x, x is also continuous. So, we have just two continuous function, and you subtract these two continuous function, of course, you will get a continuous function. So, the phi is continuous, so we do not need to worry. Similar argument for the differentiability, x is differentiable, f is differentiable. So, this phi is also differentiable. So, continuity, differentiability not an issue. Now, we will check the third one. So, the phi a. So, what is phi a? Phi a is f a minus, then you have here f b minus this f a divided by the b minus a, and then we have here x there. So, we will simplify this, and then we will also compute f b, which is here f b minus, then here also f b minus this f a, and divided by this b minus a, and that will be b, and this is here a basically, right. So, once we simplify these two, we will realize that phi a is also equal to phi b for this function. That is the condition basically we are getting out of this function, that these two values phi a, which we have written here, and this phi b, which we have written here, these two are equal. So, that means all the conditions of the Rose theorem, the continuity, differentiability, phi a is equal to phi b, all are met, and then we can apply the Rose theorem, and this Rose theorem says that the phi prime c will be equal to 0 for some c in this interval a b, in this open interval a b. Well, so this f prime c, when we take the derivative, so this was the function, so we are taking the derivative. So, f prime c, the derivative of f, yeah. So, if we take the derivative of f, and then the derivative here, so this is a constant term, and the derivative of x will be 1. So, basically we are getting the derivative of this phi here, which is equal to 0, and this is precisely the Lagrange mean value theorem. So, just by defining such a function phi x, which satisfies all the conditions of the Rose theorem, we realize the conclusion of the Lagrange mean value theorem given here. There is another generalized version of this Lagrange mean value theorem, which is called the Cauchy mean value theorem. So, in this Cauchy mean value theorem, the statement is as follows: if f(x) and g(x) are two functions, both are continuous in the interval a b and differentiable in the open interval a b, and g prime x does not vanish anywhere inside the interval, then there exists a point c again in this open interval such that, so this is a more generalized version, fb minus fa divided by gb minus ga is equal to f prime c over g prime c. That is the conclusion of this generalized mean value theorem. So, here to look at the proof here, we have to again, we will follow the similar trick which we have used for proving the Lagrange mean value theorem. Here also we define a function f(x) minus fa, then this quotient here fb minus fa over gb minus ga into this gx minus ga. So, this is the or function phi x, and again one can check that all the conditions of the Rowe's theorem, that means the continuity see the f is continuous, the g is continuous. So, naturally this function is continuous because all other are the fixed values, only the gx is here, fx is here. So, fx is continuous, gx is also continuous. So, there is no problem, and then the differentiability is also done because f is differentiable, g is also differentiable. So, the phi x is continuous, it is differentiable. Only we need to check this f phi a and phi b, which is also in this case one can check, because when phi a means you have f a minus f a, which is 0, and minus here we have f b minus this f a divided by g b minus g a, and here also we have g a minus g a. So, this is also 0. So, everything is 0. So, phi a is 0, and for phi b we have here f b minus this f a, and minus here also we have f b minus this f a divided by g b minus this g a, and into again g b minus g a. So, this gets cancelled, and this f b minus f a, and here also f b minus f a. So, again phi b is also 0. So, phi a is 0, phi a is 0, and this is equal to phi b. So, that third condition of that Rowe's theorem is also met, and then we can apply that Rowe's theorem here for this function, and we will get the conclusion. Again, here something to note down, that this g b minus g a, they are not equal, because if they are equal, this phi x will not be defined, that we have to also consider. So, because the function has to be defined. So, here g b cannot be equal to g a, because if g b is equal to g a and g is continuous and differentiable, again if we apply the Rowe's theorem, this will implies that g prime c will be 0. But we have that condition that g prime does not vanish anywhere inside this interval. So, therefore, this cannot be equal, g b cannot be equal to g a, and therefore, this function is well defined. So, there is no problem about the definition of the function. Well, so the application of the Rowe's theorem, if we apply the Rowe's theorem here, that phi prime c is equal to 0, we will get the conclusion of the Cauchy mean value theorem, which is given exactly here. Well, so these are the two theorems in addition to the Rowe's theorem, which belongs to this group of mean value theorem. And coming to the geometric interpretation, so we consider the parametric representation of the two functions given here, gx and fx. So, x is equal to gt, y is equal to ft, and t in the interval a to b. So, if we draw this curve in this xy plane, so we have the point we start here GAFA, and then we go along with this and reach to GB and FB at the end of the curve. And the geometric interpretations again says that the slope of this line joining the two end points of this curve, and there will be another point in between these two points where the slope will be equal. So, for instance, here you can see that slope at this point also is equal to the slope joining the two end points there. Well, so what we have seen the generalized mean value theorem, the so called Cauchy mean value theorem, where the statement was again under this continuity and differentiability, that this FB minus FA over GB minus GA is equal to F prime C over G prime C. And why it is generalized? Because we take that function gx, if we choose this function gx is equal to x, then what will happen? This denominator will become simply b minus a, and this g prime c will be just 1. So, that will be just the Lagrange mean value theorem. So, if we take gx is equal to x, then this Cauchy mean value theorem will become Lagrange mean value theorem. And what will happen to this Lagrange mean value theorem? If we choose our function, or if our function satisfies, this is a particular case of the Lagrange mean value theorem where the function value f a is equal to f b. So, this becomes 0 and we get the Rose mean value theorem f prime c is equal to 0. Well, let us go to the example, few examples for where we can apply these mean value theorems, in particular the Lagrange mean value theorem and the Cauchy mean value theorem. So, the first one is using mean value theorem. So, Lagrange mean value theorem basically show that cos e power x minus cos e power y is less than or equal to the absolute value of x minus y, where x y are less than equal to 0. So, we will show this. Well, we consider f t is equal to cos e power t, because we can see that the direct application of the Lagrange mean value theorem in the interval x y will lead to such expression cos e power x minus e power y. So, also we assume that x is not equal to y, otherwise when x is equal to y, of course here the equality will hold. So, both the side you will have this 0 0. So, we will have equality. So, we assume that x and y are not equal, and in that case if we apply now the Lagrange mean value theorem in this interval x y, what will happen? Cos e power x minus cos e power y over x minus y is equal to f prime c. So, there will be a point c in x y where this quotient will be equal to f prime c, that is the Lagrange mean value theorem. So, having this, we can now take the absolute value of cos e power x minus cos e power y will be equal to the absolute value of x minus y and the derivative of f at c. So, the derivative of f. So, we have cos e power t. So, we have minus sine e power t into e power t, and then with the absolute value at c. So, we have here e power c and sine e power c. So, c is between x and y are less than equal to 0. So, naturally the c is a negative number. So, whatever this sine of e power c will be bounded by 1, and e power c, and c is a negative number. So, here we will have this less than 1, the value of e power c will be less than 1. So, in that case what we have, we can bound now this by x minus y, and the maximum of this e power c and sine e power c, and c varies from x to y, right, c is in x to y. So, without much calculation, because one way could be that we get exactly the what is the maximum of this e power c sine c, but we can have rough estimate that this will be definitely bounded by 1, because sine is always bounded by 1, and this e power c will be also strictly less than 1 for c negative. So, definitely this here will be strictly less than 1. Well, so with this argument we conclude that this cos e power x minus cos e power y will be less than x minus y, will be less than x minus y. This is the result which we want to show in this example 1. Example 2 is all about again finding some value of the function where some details of the function is available, like the function is differentiable in this interval minus 2 to 2. The function value is also known, at minus 2 it is 1 and f2 it is 5. Other condition we have that the derivative of f is bounded by 1. So, f prime is less than or equal to 1 for all x in this interval minus 2 to 2. Using mean value theorem we find the value of f0. So, using Lagrange mean value theorem, we because f0 we need to find. So, we will break our interval into two parts, one from -2 to 0 and then 0 to 2, and we apply 2 times the Lagrange mean value theorem. So, naturally this f0 will appear there, and we will see whether we can estimate, we can find the value of f0 in this case. So, first we apply -2 to 0, -2 is known, the other 2 is also known. So, f0 minus f minus 2, 0 minus -2 is equal to f prime c1 somewhere in this interval -2 to 0, and then so we have this f prime c1 is, because f prime x is bounded by 1. So, we can say that this expression here f0 minus f minus 2 divided by 2. So, basically f0 minus this f minus 2 is 1, f0 minus 2 divided by 2 is equal to that derivative, and derivative is bounded by 1. So, we can say that this here is between -1 and 1 because of the derivative, the boundedness of the derivative is given to us. So, from here what we get that f0, so here we will get -2 less than this f0 minus 1 and then 2 and 1, we will add both the sides. So, we will get the inequality that f0 will be greater than -1 or equal to -1 or less than equal to 3. This inequality we get. Now, we apply the Lagrange mean value theorem in the other interval 0 to 2, and there what we see that we have f2 minus f1 divided by 2 minus 1 is equal to f prime c2, where with a similar argument, because the derivative value is known to us, this is bounded by 1. So, here also we will apply that this f2 and then minus f0, f2 is 5. So, f2 is 5. So, 5 minus this f0 is not known. So, we have f0 divided by 2, it is greater than 1, -1 and less than 1. So, this is -2, 5 minus this f0 and less than 2. So, here we say -5 both the sides in every expression. So, -7 f0 and then we have here -3 when we add here -5. Well, so with this what we get, that 7, now we are multiplying by -1. So, the inequality will change. So, f7 is greater than f0 and greater than this f0 is greater than 3. So, what we are getting at this point, that f0 is greater than equal to 3. From the earlier inequality we were getting that f0 is less than equal to 3. So, from these two inequalities we can find out that f0 has to be 2, because in this part when we apply the mean value theorem we got f0 has to be less than -3. When we apply the Lagrange mean value theorem in the other interval 0 to 2, we realize that f0 has to be greater than 3, and we mix the two. If we merge the two, we get that f0 has to be 3. There is no other possibility than f0 being 3. So, another example where we have the function 0 to 1 is defined, the real valued function. It satisfies that f prime is given as 1 over 5 minus x square, f0 is given as 2, and using Lagrange mean value theorem we will estimate the bounds for f1. So, this is also a similar example like we have done before, where we will be doing we will be using the idea of the given derivative. So, the bounds on the given derivative. Earlier problem it was given that f derivative is bounded by 1. Here we have to see the lower bound and the upper bound for this derivative, and with the help of this at least we can find the bound of f1. So, we need to apply the Lagrange mean value theorem on this interval 0 to 1. The 0 value is given and 1 we will estimate. So, we have f1 minus f0 over 1 is equal to f prime at c. for some c 0 to 1. So, what we realize here that f1 minus f0 is 2 is equal to f prime c. Well, and the derivative f prime c we have already there, it is 1 over 5 minus the c square now, and this can be estimated. We can have the lower bound, we can have the upper bound on this derivative 1 minus 5 x square. So, we have 1 over 5 minus c square, and c is between 0 and 1. So, here we can easily estimate this, that when this c will be 0, for instance, the minimum 1. So, we have the lower bound 1 over 5, and when you put here c to 1, so we have the minimum value here in the denominator, that will lead to the upper bound. So, that is 1 over 4. So, this derivative here is between 1 by 5 to 1 by 4, that information we know from the derivative now, and the derivative is here f prime c. So, f1 minus 2 is between then 1 by 5 and 1 by 4, because that was the derivative f prime c is equal to f1 minus f2. We have got this from the Lagrange mean value theorem, and the range for this derivative, the lower bound or upper bound, we have obtained here from the given information. So, that means this f1 minus f2 is bounded above by 1 by 4 and below by 1 by 5. So, here we can easily estimate that our f1, so this 2 will go to both of them. So, here 11 by 5 and there 9 by 4. So, this f1 is more than 11 by 5 and less than 9 by 4. This is the conclusion here, that f1 will be somewhere in between. We do not know the exact value here, because the function from the Lagrange mean value theorem we can get only this information on the bound of this O1. Well, so we have one more example here, where the function x cube minus 5x square minus 3x is given. Apply Lagrange mean value theorem in the interval this 1 to 3 and find the value of the parameter c that appear in the theorem. So, we have that f prime c there. So, this we will get in this example for the Lagrange mean value theorem. So, according to the mean value theorem, so this is a straightforward question, where we have f prime c is equal to f b minus f a over b minus a. So, we have applied this in the interval 1 to 3. So, f 3 minus f 1 over 3 minus 1, this is 2 here, f 3 we will compute, this is minus 27, f 1 will come as minus 7 and then 2 there. So, this evaluation, once we evaluate this, we will see that this is minus 10. So, f prime c is minus 10, and f prime we can get from here also. So, the f prime c we will get from direct from the function, which is 3c square minus 10c minus 3 is equal to minus 10, and we solve this. So, we will get two numbers for c which satisfy this equation. C is 1 and 7 by 3. So, the c has to be in the interval in the open interval 1 to 3. So, it cannot be 1, it cannot be 1, it has to be between 1 and 3. So, the 7 by 3 is the number which we were looking for. So, this c is 7 by 3, which is exactly that c which comes in the mean value theorem, Lagrange mean value theorem. So, this is the last example. So, let this f be a differentiable, and here the a we have taken positive. Using appropriate mean value theorems, show that there exists C1 C2 in the interval a b, such that f prime C1 over a plus b is equal to f prime C2 over 2 C2. So, this is also a direct application of the two mean value theorems we have studied, but we have to see that how to use those mean value theorems so that we get this desired result. So, first let us apply the Lagrange mean value theorem in the interval a to b and see what we get. So, f prime, and we call this parameter C1, is equal to f b minus f a over b minus a, and this C1 will belong to a comma b. So, this is the direct application of the Lagrange mean value theorem, which says that this quotient is equal to f prime C1. But here in the conclusion of this example, we want to see this here a plus b and here 2 times C2. So, if we remember, we have the generalized mean value theorem, where f and g, 2 functions are given, and g we can choose whatever we want. So, if we choose g is equal to x square, and the g prime will become 2x. So, which is coming exactly here 2c, and there also we will have b square minus a square. So, from there we will also get a plus b, because the rest will merge into the f prime C1. So, if we apply there fb minus fa over gb minus ga f prime C2 over g prime C2, where C2 is equal to C2 belongs to this interval, the open interval a comma b. So, here what we apply this. So, we have fb minus fa over b square minus a square, because g x is x square, and then we have the derivative f double derivative at C2 and g double derivative at C2, that means x square. So, 2x, so 2C2, and this is exactly what we were looking for, because fb minus fa over b minus a. So, here that will become f prime C, and so this is f prime C, and then we have here a plus b, because this is b minus a, b plus a. So, this is a plus b will remain, and b minus a will be absorbed here in f prime C1, and the right hand side is precisely f prime C2 over 2C2, which is the conclusion of this result here, f prime C1 over a plus b f prime C2 over 2C2. So, what is the conclusion of this lecture? So, we have gone through 2 mean value theorems. The one was the generalized mean value theorem, where we have considered 2 functions f and g having all these continuity differentiability assumptions. So, fb minus fa over gb minus ga is equal to f prime c over g prime c, and if we take this g x is equal to x, we get another particular mean value theorem, which is called the Lagrange mean value theorem, and the conclusion was that this f prime c is equal to fb minus fa over fb minus a. So, with this we have completed all 3 mean values theorem in lecture 1, Rowe's theorem, and then in this lecture the Lagrange mean value theorem and also the Cauchy mean value theorem. So, with this, here are the few references which we have used for preparing this lecture, and I thank you for your attention listening this lecture. Thank you so much.